Okay, guys, so now we're on to section 6.2, which is about binomial random variables. So a couple things to tell you. So first of all, in section 6.1, was like, well, it's true for any random variable. So it's just general random variables, section 6.1. Everything in 6.1 is true for any random variable. But in section 6.2, we're going to look at one specific random variable called a binomial random variable. Okay, so stuff that's in this section can only be done in a certain situation. And that's very important for exams and especially the final. I guess the final is the one in particular that I really worry about, because a lot of times when I give a binomial problem on the final, people leave it blank because they don't know, well, what problem is this? What kind of problem is this? So that's the first thing we're going to work on today. What is the binomial random variable situation? Like, how can you tell that the problem is a binomial random variable problem? Once you can tell that, then I'm going to show you exactly how to do the problem. But I think more important is you read the problem and go, oh, that's a binomial. Okay, so that's the idea. Let me say it one more time. The stuff we're learning in this section is not true for every random variable. This is one specific, one special situation of a random variable called a binomial random variable. Okay, so basically the first thing I'm going to tell you is that in any binomial random variable, there's four things you need to look out for, four ingredients. And if you see these four things, then you know it's a binomial problem. Okay, so the first thing that you look for in any binomial problem, it has to say, the problem has to say, you're going to do something this many times. Like, you're going to repeat something over and over again, and here's how many times you're going to do it. Like, I'm going to flip a coin 20 times, or I'm going to draw a card out of a deck of cards 80 times. They're going to say you're going to do something and you're going to repeat it, and they're going to tell you how many times you're going to repeat it. The amount of times you're going to do it total is called little n. So what we're going to do is I'm going to give you three examples, and we're going to look for all these four ingredients, but we're just focusing on the first one. Check out this problem. This is a binomial problem. It says when flipping a coin 20 times, what's the probability the coin will land on heads exactly 12 times? I don't want the answer right now, okay? But just tell me what we're repeating, what are we doing, and how many times are we doing it? Someone tell me that. So what are we doing? And then I want you to tell me how many times we're doing it.
We're flipping a coin 20 times?
That's right. So the thing we're doing is we're flipping a coin. We're going to repeat that over and over again 20 times. That means in this problem, little n is 20. Okay, we'll come back to this problem. Let's go and look at another one. Here's another example of a binomial problem. Again, all I want you to look for in this problem right now is that it says you're doing this and you're going to do it this many times. Okay, you're about to draw a single card from a deck of cards 80 times with replacement. What's the probability you will draw exactly 28 hearts? Again, we're going to look at the rest of the problem later. All I want to look at right now is what are we doing and how many times are we going to repeat it total? Someone tell me.
Drawing a single card from a deck 80 times?
Yeah, so we're going to draw a single card from a deck of cards, and we're going to do that over and over again 80 times. That means little n is 80. It's how many times we do it total. I know there's another number here. We'll get to that later. But n is how many times we do whatever we're doing total. Let's go look at a third example. 10 students from this class are going to be selected. What's the probability exactly 8 of them own an iPhone? That's a binomial problem. And again, to know it's a binomial problem, there's four things you look for. I'm just looking for the first thing for right now. In this problem, who can tell me what are we doing and how many times are we doing it? This one might be slightly tricky. Go ahead.
Selecting 10 students?
No. This one's slightly trickier than the other ones. Just slightly trickier. What are we doing and how many times are we doing it?
We're selecting students from a classroom 10 times?
Okay, that's better, yeah. So we're selecting, so the thing we're doing is we're selecting one student. I know it doesn't say one student. We're selecting one student and we're going to repeat that 10 times. So when they say you're going to select 10 students, think about it like that. Is we're selecting one student and we're going to do that over and over again 10 times. So this problem n is 10. Okay, you guys with me so far?
Yes.
Okay, so that it has to say something like that in the problem. You're going to do something, you're going to repeat something over and over, and here's the amount of times you're going to do it total. That it has to say that in the binomial problem. Okay, The second ingredient, second thing you look for, even though we're going to do something over and over again, every single time you do it, the result can only belong into one of two categories, and they call those categories success and failure. I don't know why they call it success and failure. They could have called it just category A and category B. Don't think of success as a positive thing and failure as a negative thing. It's not like that. But every single time, again, I know we're not doing something one time. We're going to do something a bunch of times. But every single time you do it, the result is either a success or a failure. What's a success? What the question asks you about. Everything else is a failure. Let's go ahead and look at the first example again. When flipping a coin 20 times, what's the probability the coin will land on heads exactly 12 times? Okay, every single time, I know I'm flipping the coin 20 times, okay, so n is 20, but every one time I flip, every single time I flip, when I'm done, it's either a success or a failure. It's a success if it lands on what? Any ideas?
Lands on
Land
head.
on heads.
If it lands on heads, because that's what the question asks you about. It asks you about heads. So when I flip the coin, if it lands on heads, it's a success. If it lands on tails, it's a failure. Okay, so every time you flip a coin, there's only two results, heads or tails, success or failure. But how do I know heads is a success, not tails? Because heads is what they asked about in this question. Let's go to the next one. So back to this one. You're about to draw a single card from a deck of cards 80 times with replacement. What's the probability you draw exactly 28 cards? 28 hearts. Okay, I'm drawing 80 cards. So I'm doing something 80 times total. But every single card I draw is either a success or a failure. If I draw a card, it's a success if it's what?
If it's a heart.
Yes, I'm drawing one card. I'm looking at it. If it's a heart, I got a success. If it's not a heart, it's a failure. Again, why is a heart success? Because that's what they ask us about. When they ask us the question, what's the probability of getting 28 hearts? But they're talking about hearts. So if it's a heart, it's a success. Not a heart, failure. So everybody with me on this?
Yes.
Yeah, let's go to the third one. Okay, again, 10 students from this class are going to be selected. What's the probability that exactly 8 of them own an iPhone? Again, think of it as I'm selecting one student. I'm going to do that over and over again 10 times. But even though I'm doing something 10 times, every single time I select a student, I get a success or a failure. I get a success if what?
If they have an iPhone.
If they own an iPhone, yeah. And if they don't own an iPhone, then it's a failure. Every single time. So since I'm doing something 10 times, I'm going to get 10 successes and failures. But every single time I do whatever I'm doing, it's either end up with a success or a failure. A success is what they ask about. So in this case, owning an iPhone, that's a success. And that's why it's called binomial. Bi means two, meaning every single time you do it, there's only one of two results, success or failure. Is everybody with me so far?
Yes.
Okay. Let's go to the third thing you have to look for. Every trial has to be independent of every other trial. There has to be independence. When I say every trial, I mean every time you do the thing, because we're doing something a bunch of times, every single time you do it has to be independent of every other time. What that basically means for us is if we're drawing something out of a bag, let's say more than once, we got to be doing it with replacements so that we have independence, because we talked about that before, that word independence. If you draw more than once with replacement, we have independence. So something like that is what's happening. Let's take a look at this first one. When flipping a coin 20 times, what's the probability the coin will land on heads exactly 12 times? We're flipping a coin over and over again, and each flip is independent of every other flip. There's a couple of ways to say that. One way to say it is, when you flip a coin, the next time you flip it, the result doesn't depend on the previous flip. It's not like, oh, it landed on heads last time, so it'll probably land on tails this time. It doesn't work like that. Every single time you flip a coin, it's 50-50 if it lands on heads or tails. Another way to say it is, I've already told you that every time you do an experiment, every experiment is equivalent to drawing from a bag. If you're flipping a coin, it's like you're drawing once out of this bag. And if you flip the coin once, let's say it lands on heads. So it's like you drew the heads out of the bag. But when you go to flip it again, heads is possible again. What that means is it's like you put it back. So it's like it's with replacement. Okay, so every flip is independent of every other flip, or it's like we're drawing out of this bag with replacement. So we have independence there. Let's go to the next one. This one, it says it, shouts it at you, right? You're going to draw a single card from a deck of cards 80 times with replacement. So it says that. So we have our independence there. In other words, every draw is independent of every other draw because we're drawing with replacement. Let's go look at the third one. 10 students from this class are going to be selected. What's the probability exactly 8 of them own an iPhone? Now, and this problem's written, it's not so good, you know, like, and they do this sometimes in this section. So let me say this much. If it's not clear in the online homework, if the draws are done independently or like with replacement, you're going to pretend that it is. We're going to assume it even if they don't say it. It's annoying. On quizzes or exams, I'll hopefully make that more clear than they will in the online homework, but they'll write something like this. It's a little bit unclear. When you select 10 students, would I select the same student more than once? Maybe not. But if I put everybody's name in a hat and I draw one name at a time, put it back, I could get the same student more than once. So am I drawing with replacement or without replacement? So again, in a binomial, it's got to be, we have to have independence. So when they say 10 students are selected, they mean one at a time with replacement, even if they don't say it. So again, I know that's a little bit annoying, but I just want to make sure that's clear because that'll happen in online homework. So we're assuming it for every problem in the section, whether they say it or not, but I'll make it more clear on a quiz or an exam that it's independent. Okay, fourth thing you look for. The problem has to say, what's the probability of getting this many successes? Let's go read the problems again. Here's the first one. When flipping a coin 20 times, what's the probability the coin will land on heads exactly 12 times? We've already said in this problem, if the coin lands on heads, it's a success. If the coin lands on tails, it's a failure. And now the question says, what's the probability that we'll get exactly 12 successes? Landing on heads is a success. And if I ask you what's the probability of getting that many successes, that's a binomial problem. Let's go to the next one. Again, you're about to draw a card from a deck of cards 80 times with replacement. What's the probability you draw exactly 28 hearts? We already said that drawing a heart is a success. I'm saying what's the probability of getting 28 successes? Okay, so if that's what the question asks, what's the probability of getting this many successes? That makes it a binomial problem. Let's go to the third one. Again, 10 students from the class are going to be selected. What's the probability exactly 8 own an iPhone? I'm asking you, what's the probability of getting this many successes? Because in this problem, we said successes owning an iPhone. So if you see those 4 ingredients in the problem, that makes it a binomial problem. Do I have it here? Yeah. So again, these are the 4 things you look for in every binomial problem. The problem has to say, you're going to do something and you're going to repeat it a bunch of times. And they'll tell you how many times you're doing it, and that's what n is. N is how many times you're doing it total. Second thing you look for is, even though you're doing something a bunch of times, every single time you do whatever you're doing, the result has to be a success or a failure. It has to be, the result has to land in one of 2 categories, success or failure. And success is what the question asks you about. Every trial, every time you do whatever you're doing has to be independent of every other time. So again, if we're drawing with replacement. Even if they don't say it, that's what we're doing. So if the problem comes from, if you know for sure the problem is from section 6.2, then it's independent whether or not they say it. But on the final, for example, I'll have to make it clear that they're independent because you'd be like, well, what section is this problem from? Kind of thing. And then the most important thing, the question has to say, find the probability of getting this many successes. And then it's a binomial problem. Okay, so that's a big part of the battle, reading the problem and just reading it and going, okay, I see all these 4 things happening, so this is a binomial problem. When you're doing the problem, you do this stuff in your head. There's going to be other stuff you're going to have to write down. There's going to be a lot you're going to have to write down. But you do all this stuff in your head just so you can say, okay, I recognize this is a binomial problem. Questions so far? Okay. So we're going to look at this example. This This is a preliminary example. This is not the main example that we're going to do. This is a preliminary example so you can get an idea of what's going on here. It says a bag contains two kinds of balls. Each ball either has the letter S on it for success, those are the green ones in the bag there, or they have the letter F for failure, those are the red ones. So every time you draw out of the bag, you either get a success or a failure, you get a green or a red. Now it says, suppose you draw 5 balls from the bag with replacements. Let X, the random variable, be the total number of successes you draw from the bag. What's the probability you get exactly 3 successes? Okay, I want to do a bunch of things here. First thing I want to do, and again, this is just so we understand the story. I want to first go through the 4 ingredients so that we can know that this is a binomial problem. The first one says we have to do something over and over again, and they're going to tell us how many times we're doing. In this problem, tell me, what are we doing, and how many times are we doing it total? So what are we doing in this problem? And how many
Drawing
times-
5 balls from the bag with replacement.
Okay, so when you tell me that, you need to tell me what we're doing and then how many times we're doing it. So the 5 is how many times we're doing it total. Okay, so the thing we're doing is we're drawing 1 time from the bag. Okay, and we're going to repeat. So when they say you're drawing 5 balls out of the bag, I want you to think about that as we're drawing once out of the bag, and we're going to repeat that process 5 times.
Gotcha.
Okay, so we're drawing once out of the bag, and we're going to repeat that a total of 5 times, and little n is 5 in this problem. So are we with me here?
Yes.
Okay. Second thing is, let's look for success and failure. That's pretty clear. Every single time you draw from the bag, you either get a success or a failure. You either get a red or a green. Oh, sorry, green or red, success or failure. Okay, so that's good. Third one is, there has to be independence. The independence is coming from the part that says with replacement. We're drawing with replacements. We have independence there. And the problem has to say, what's the probability of getting a certain amount of successes? In this case, what's probably getting 3 successes? So this is definitely a binomial question. Okay. The next thing to tell you is, you remember how I told you a random variable is a way of changing the names of the outcomes to numbers? These are not the outcomes, okay? Because we're not drawing once. If we were drawing 1 time, these would be the outcomes. So I want to make sure we're clear. So let's take just a minute or two. I want to write down some outcomes so we understand what the outcomes of this experiment look like. And then I want to write down what the value of X is for that outcome. Okay, so what are we doing? We're drawing 5 balls from the bag. When you draw 5 balls from this bag, here's an outcome you could get. You ready? You can get S, S, F, S, F. It's like, instead of flipping a coin 5 times where you get heads and tails symbols, I'm going to get either an S for a success or a failure. Every single time I draw, I get a success or a failure. We're drawing 5 times. This is what an outcome looks like. Are you guys following me?
Yes.
Yes.
Yeah. Okay. And then what is this binomial random variable doing? What a binomial random variable does is it counts how many successes you have. Just like earlier we saw, you flip a coin, we're going to count how many times it landed on heads. Well, binomial counts how many times it lands. It's a success. Look what it says. Let X be the total number of successes. That's what X always is in every binomial problem. Total number of successes. So for that outcome, what's the value of X?
3.
3. It just looks at the result here and counts how many times you see an S. Let's do another one. How about, here's another outcome. S, F, F, S, S. And tell me the value of X for that one.
3.
3. Here's another one. S, 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 S. So every time we drew from the bag, we got a success. What's the value of X for that one?
5.
5. Let me do a couple more. S, F, S, S, F. What's the value of X for that one?
3.
3 again. How about F, 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 F?
0.
0. Yeah. And anyway, there's lots of them. I'm not going to list them all, because there's lots of things here. So the random variable counts in a binomial problem. The random variable counts how many successes you ended up with. If I ask you, what are all possible values of X? I could make 2 bags, okay? I can make a bag out of these and a bag out of these. We'd have 2 bags, okay? But if I say, what are all possible values of X? Someone tell me the smallest possible value of X.
0.
0. In other words, the amount of successes you can have, the minimum is 0. That means you flip the coin. I'm sorry, you drew from the bag 5 times and you got 0 successes. Could you get 1 success?
Yes.
Yeah. It'd mean 1 of the times you drew a success, the other 4 were failures. Could you get 2 successes?
Yeah, you can have 2.
What's the highest you can have?
5.
5.
5. Could you have like 7 point, or okay, could you get 3.9 successes?
No.
No, because it has to be a whole number. It's going to count 1, 2, 3, 4, how many successes you have. So the possible values of X are 0. Please don't forget 0. Students often forget the 0. You could get 0 successes or 1 or 2 or 3 up to however many times you're drawing total, in this case 5. So it's got to be a whole number, and it has to be between 0 and 5. Okay, you guys with me so far?
Yes.
Okay. The question asks us, what's the probability of getting exactly 3 successes? Since 3 is one of these, we can ask what's the probability of getting 3 successes. The notation will be probability capital X equals 3. Remember what X stands for? It's a total number of successes. What's probably the total number of successes is 3. So what's the probability of getting something like this or this or this? You know, the ones where we see 3 over here. That's what the question is. I'm going to show you some of the things you're going to be writing down, but I'm not going to write them down just yet. There's 7 things I want you to write down every time you're doing a binomial problem. The first word you're going to write down is you're going to write down the word binomial. Lets me know you know it's a binomial problem. Other than writing the word binomial, there's going to be 6 other things I'm going to want you to write down. 4 of them, to figure them out, you need to forget that you're doing something. In this case, we're doing something 5 times. Pretend you're doing something 1 time to figure out these things. Okay, so what are you going to write down? So you're going to write down what a success is in words. In this problem, when you draw 1 ball, it's a success if you get a green one. So it's drawing a green ball. But again, to figure out what a success is, forget that the problem said we're drawing 5 balls and just pretend we're drawing once. If we're to draw once, how do you know it's a success? If it's green. If it's one of the ones that has the S on it, then it's a success. Okay, so you can write what a success is in words. In every binomial problem, you can write down what a success is in words. You can write what a failure is in words. In this problem, a failure is getting a red ball or getting one that has an F on it. And again, to figure out what a failure is, pretend you're drawing once or you're doing whatever they say 1 time. Okay, so you can write down what those things are. Then you can write down little p. Little p is the probability of success. When you're trying to find the probability of success, again, pretend that you're drawing once. If you draw 1 time out of this bag, what is the probability you get a success? Someone tell me. You draw once out of the bag. What is the probability you get a success? Anyone?
Is it 5 out of 7?
5 out of 7, right. So little p is the probability of success when drawing once. It's 5 out of 7 in this example, okay? In other examples, you might have to find it on your own, like you found the 5 out of 7 right here. And in some problems, they'll give you the number in the problem. They'll just tell you what it is. So you got to figure out what that is. Then you got to figure out what little q is. Little q is the probability of failure. And again, to figure out each of these 4 things, pretend you're drawing once. So if you draw once out of the bag, what's the probability of getting a failure? Take a look at this bag. What's the probability of getting a failure if you draw 1 time out of the bag?
Two out of 7.
2 out of 7. There's 2 failures, 7 total. So in this problem, it's 2 out of 7. So you got to write down those 4 things. I want you to write those things down at the beginning before you start the problem. After you write those 4 things, 2 more things, These other two things, to figure out what they are, forget that, don't think of drawing once, think of drawing the amount of times they tell you in the problem. In this problem, they say you're drawing 5 times. You're gonna write down little n, which I already told you is how many times you're doing whatever you're doing. So in this problem, little n is 5. So it's the total number of balls drawn. In this case, you're just gonna write 5, but it depends on your problem. And then you're gonna write down what capital X is. With the random variables, you're gonna write that out in words. When you write it out in words, it's always gonna be the total number of successes, okay? So it's a total number of successes drawn, but when you do a problem, I don't want you to write the word success. I want you to write what a success is. In this problem, a success is just a success, but in like the other problems, you instead of saying total number of successes, you write total number of times the coin landed on heads, because the landing on heads was a success. Or what was the second example? Total number of times you drew a heart, because drawing a heart was a success. So don't write the word success, write what a success is in whatever problem you're doing. The third one would be total number of students that own an iPhone, okay? Because, so X is always the total number of successes, but don't write the word success, write what a success is in your problem. After you write those things down, then we can do the problem. Okay, so now the next part of this discussion is I'm gonna derive a formula for you for how to find the probability that they're asking us for. Okay, so let me remind you what the question was. Okay, we'll just leave the picture here. So the question said, we're gonna draw 5 times from this bag, find the probability of getting exactly 3 successes. That was the question. We're drawing 5 times, one at a time with replacement, so we know what the outcomes look like. It's a sequence of F's and S's, okay? And sometimes you'll have 3 successes, sometimes you'll have more, sometimes you'll have less. You can have 0, 1, 2, 3, 4, or 5 successes. What was the probability you end up with exactly 3 successes? That's the question. Now remember, X is the total number of successes, so the notation for this is probability that X is 3. Probability that the total number of successes you get is 3. So that's the notation. There's a notation. Now, this next stuff you are not gonna do. Just kick back for a couple minutes and listen to what I'm saying. I'm gonna derive a formula for you, and I'm gonna try to show you that it comes from the stuff that we learned in chapter 4. So what we're gonna do is we're gonna rephrase the question. I'm gonna say, how can we get exactly 3 successes? Well, one way to get exactly 3 successes is this way. Take a look at what this says. It says the first draw is a failure, and second draw is a failure, and the third is a success, and the fourth is a success, and the fifth is a success. The little subscripts are which draw I'm on. And again, first, so failure and on the first, and failure on the second, and success on the third, and success on the fourth, and success on the fifth. Do you guys agree if that happens, I get exactly 3 successes? Do you guys agree?
Yes.
Yeah, but that's only one way to get exactly 3 successes. So now I have to list them all. So now I'm gonna write or, okay? Now here's another way to get exactly 3 successes. Failure on the first, and success on the second, and failure on the third, and success on the fourth, and success on the fifth. That's also exactly 3 successes out of the 5 draws. Or, and I have to list them all. Here's another way. Notice again, there's exactly 3 successes there. Or, and after you list them all, you get this mess. Again, you're not going to do it this way. Just understanding, rephrasing the question. Notice how I rephrased it. We have all these ands and ors in here. Now what I'm going to do is I'm going to apply the or formula. So there's all these ors. So apply the or formula. The or formula says you do the probability of each thing separately and then you add. That's only true if the events are disjoint, but the events are disjoint because this result and this result can't both happen. Okay, because if this first result happened, for example, then the second outcome is a failure. But if this result happened, the second outcome is a success. You can't have both of those happen. And if you just look at all pairs, they're all disjoint. So we do the probability of each one separately and add. So it's going to be probability of the first mess plus probably the second mess plus probably the third mess. Do it for each one, we get this. So now I applied the or formula. Now I'm going to apply the and formula because this is a probability of an and. We have 2 and formulas depending on if the events are independent or not. In binomial problems, the events are independent. So we can use the shorter and formula, which says, like, so to do this probability here, you can do the probability of the first times, for and you do times probably the second, times probably the third, times probably the fourth, times probably the fifth. No conditional probabilities. because the events are independent. So now it's going to go like this, probably the first, times probably the second, times probably the third, times probably the fourth, times probably the fifth. That is just this mess over here. Plus, now we got to do it for this. Same thing, probably the first, times probably the second, and do it for all of them, you get this mess. So it's a mess so far. Let's keep going. So there's the mess. I moved it up. And now let's see. This is the probability the first draw is a failure. The probability the first draw is a failure is 2 over 7 in the example we just did. But in general, the probability we get a failure, we're calling that Q. Q stands for probability of failure. So that probability is Q. This probability is also Q. This probability is P, because P is probability of success. And this is also a P, and this is also a P. So we have Q times P times, so Q times Q times P times P times P, plus, for the second one again, every time it says probability of failure, I'm going to put Q. So these are Q's. And then the ones that are successes, I'm going to put P's. So the second one goes like that, and there's all of them. Okay, so we're here now. So now the next thing is every term has 3 P's and 2 Q's. It makes sense because everything I've listed had 3 successes, because I'm asking probably getting 3 successes. So there's 3 successes, and if we're doing something 5 times and we got 3 successes, then the other 2 have to be failures. So every term has 3 P's and 2 Q's in it. So we just clean it up. The first term is P cubed Q squared, like 3 P's, 2 Q's. Second term, 3 P's, 2 Q's. They're all 3 P's, 2 Q's. And then now you just have to count how many we have. And if you count them, you see there's 10 of them. So it's 10 P cubed Q squared. So I kind of showing you where the formula came from. So this nasty thing we went through went all the way down to this little simple thing over here. So it's 10 P cubed Q squared. So if you want to find the probability of getting 3 successes, you're going to do P to the power 3. Why P to the power 3? Because P stands for success. So think of this as 3 successes. And then it's going to be 2 failures, because if there's 3 successes, the other 2 are failures. Okay? So 3 successes, 2 failures. And then the only thing left to do is figure out where does this 10 come from. I figured out the 10 because I listed them all. I listed all the different ways to get it, and it turned out there were 10 of them. But you don't want to list them all. So how do we get this 10? Okay, so how do we figure out the 10? So here's the answer. The answer is, it comes from a section in the book that I skipped. When we did the counting section, it was section 5.5, where I did multiplication rule for counting. Multiplication rule for counting was not the only thing in that section. There was also a permutation rule, combination rule, factorial rule are all in that section. But I skipped that stuff. And I'm still going to skip it. Let me just tell you for now that this number is a combination. Okay? It's a combination, and what it's going to, so when you write a combination, you're going to write a C for combination. You're going to put 5 first, because that's how many times we're doing whatever we're doing, and then the number of successes are going to go here. So it's like out of 5 things that we're doing, we're going to select 3 spaces to put successes. So 5C3 is what that is. If you don't know what 5C3 is, don't worry. I'm going to show you how to find it on the calculator. But this 10 is 5C3. Again, why 5? Because we're doing something 5 times. Why 3 here? Because 3 successes is what we asked about. And so that's basically the formula. Okay, and then if you're dying to know what the answer is in this problem, then I put in what P is, which is 5 over 7, and Q is 2 over 7. And the answer in this problem, there's the answer for this problem. Okay, so if you're dying to know what the answer is, that's the answer. But what we really want to get is that this probability, you can calculate it using this formula over here. All right. So this is the formula for binomial probabilities. Anytime you're trying to find a binomial probability, you can use this formula. I will explain it all when we do an example. But just like, so the next thing is, just like last section, we talked about expected value, standard deviation, and variance. In this section, we have formulas for expected value, standard deviation, and variance. They come from the formulas from the last section. What I'm telling you here is the following. If you're trying to find expected value, standard deviation, and variance of any other variable that's not binomial, do it the way I showed you in section 6.1. And sometimes that's kind of long and kind of annoying, but that's the way you have to do it. But if it's a binomial random variable, it turns out if you do the stuff from that we learned in the last section, you end up getting these real simple formulas for expected value, standard deviation, and variance. So these are the formulas for expected value, standard deviation, and variance for a binomial random variable. But you can only use the formulas on this slide if it's binomial. Otherwise, do not use it. So you have to first know that it's a binomial problem. And if you do know that, and you want to find a probability, you can use this, or you want to know the expected value, standard deviation, or variance, then you can use those formulas. Otherwise, do not use them. And on that note, let's do a problem. Example 1, let's see what it says. Suppose you are going to draw 10 cards from a standard poker deck with replacement. Part A says, what's the probability that exactly 7 of the cards are number cards? Just reading the top sentence and then part A lets me know it's a binomial problem. Let's go through that real quick. First of all, let me read the problem again. Suppose you're going to draw 10 cards from a standard poker deck with replacement. What's probably exactly 7 of the cards are number cards? My first question is, so I'm going through the 4 ingredients of a binomial problem. What are we doing in this problem? What are we repeating over and over? And how many times are we doing it total? So what's the thing we're doing and how many times are we doing it total? Someone tell me.
We're drawing cards from a deck 10 times.
Yeah, so say it like this. You're going to draw 1 card from a deck. I know it doesn't say it anywhere, but when someone says you're going to draw 10 cards, I want you to think about it as you're going to draw 1 card and you're going to do that 10 times. You following me?
Yes.
Okay, so we're drawing 1 card. That's the thing we're doing over and over again. We're doing it 10 times total, and that means n is 10. Okay, second ingredient, even though we're doing something 10 times, every single time we draw a card, once we get the card, we can look at it and go, it's a success or it's a failure. It's a success if it's what? You got to read all the way to part A to know what a success is. So when I draw 1 card, I show it to you. It's a success if it's what?
If it's a numbered card.
If it's a number card. If it's got a number on it, it's a success. If not, it's a failure. Okay. Third ingredient, independence. Where's the independence?
With replacement.
With replacement. And the fourth thing is the problem has to ask you to find the probability of getting a certain amount, a certain amount of successes. And number card is success. So this is a binomial problem. And anyway, part A, B, C, and D are binomials, and then we have some other stuff to do. But let's go to this. Okay, every time you do a binomial problem, before you actually do the problem, I want you to write down 7 things at the beginning. Here's what you're going to write down. You're first going to write down the word binomial. I want you to write binomial. That lets me know you know it's a binomial problem. Then there's 6 other things you're going to write. And you're going to write this whether I ask you or not. Okay, so please don't forget to write it. Sometimes I'll say, don't forget, write these things down. And if I don't, write them anyway. So now you're going to write down what n is, which is how many times we're doing whatever we're doing total. What's n? Someone tell me what n is.
10.
10.
Because we're drawing 10 cards total. That's n. Okay. Then you're going to write down what a success is. When you write down what a success is, you're going to write this in words. And when you're trying to figure out what a success is, I want you to forget that we're drawing 10 cards and imagine we're drawing 1 card. When I draw 1 card, anytime I draw 1 card, it's a success if it's what? If the card is what?
A number.
A number card. So success is if the card is a number card. And I want you to write something to make it obvious this is when you're doing it once. When you draw 1 card. So every 1 card, if it's a number card, it's a success. Then you're going to write down what a failure is. Again, to figure out what a success and what a failure is, you have to forget momentarily that you're drawing 10 and imagine you're drawing once. If you draw once, it's a failure. If the card is not a number card, you can just write if the card is not a number card. Or I'm going to write if the card, so what are the cards that are not number cards? If the card is a face card or an ace, those are the ones that are not number cards when you draw 1 card. And to figure out these things, and the next 2 things I'm going to write, think about drawing once, even though we're not drawing once in this problem. The next things you're going to write down, you're going to write down what little p is. Little p is the probability of success. So I want to know what's the probability of getting a number card when you draw one card. When you're trying to figure out little p, imagine you're drawing just one card. What's the probability to get a number card? Someone tell me. Well, tell me the bottom number. What's the bottom number?
52.
There's 52 cards total. And to get the top number, you got to tell me how many number cards there are. How many number cards are there?
40.
Oh, you're close.
36.
36. Yeah. 4, 2. You have to count the 2s, 3s, 4s, 5s, 6s, 7s, 8s, 9s, and 10s. So it's 9 cards, but with 4 suits gives you 36 cards. Then you got to find little q, which is the probability of failure. Bottom number is 52 again. The top number, you have to count the face cards and the aces. How many cards?
$16 cards.
Yep, 16 cards. So it's 4 aces, 4 jacks, 4 queens, 4 kings. And again, for these two, again, you think about drawing once. So for those 4 things, what's a success, what's a failure, what's little p, what's little q? Forget that we're drawing 10 times. Pretend we're drawing 1 time only. Okay, and you figure out those things. And the last thing you're going to write down is what your variable is, capital X. Capital X is always the total number of successes. Okay, whenever you write down what X is, it's always the total number of successes. But don't write the word success. Write what a success is. So I'm going to write down this, the total number of number cards among the 10 selected cards. So again, we're selecting 10 cards. And after we select 10 cards, we're going to count how many of them have numbers on them. And that's what X is. It's going to count how many of them have numbers on them. So real quick, to make sure we understand this, what's the smallest value for X? So in other words, if I draw 10 cards from a deck of cards, and then I look at them and count how many of them have numbers on them, what's the smallest answer I could get?
0.
0. What's the biggest answer I could get?
10.
10. Otherwise, so the possible values of X are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's got to be a whole number from 0 to 10. Yeah. All right. So you write that down at the beginning of every binomial problem. You write down these 7 things. Then we do the problem. Part A says, what's the probability that exactly 7 of the cards are number cards? The notation is probability capital X equals 7. Remember, this is how many number cards you have. I'm saying what's the probability that the amount of number cards you get is 7. So write the notation. I'm looking for the notation. And now what you're going to do is you're going to fill into the formula. Actually, let me move this down a little bit. Okay, the formula, the binomial formula, which I will give to you, goes like this. Probability capital X equals little x. It's NCX, P to the X, Q to the N minus X. So what you're going to do is you're going to fill into this formula. Okay, for the N, it's up there. It's here. It's 10. So you're going to put a little 10. Next to it, you're going to put this capital C. And then little x. Little x here is the number that's here. So in this problem, it's 7. So you're going to put 7 there. We'll talk about the C in a minute. But 10C7. And then this is, Then it's P to the power X. P is this. So it's 36 over 52 to the power of 7. That's little x again. Little x is 7. Little x is the number that's in here. Okay, so 7. And then times Q, which is 16 over 52, to the power of N minus X. N is 10, C is 7. So you write that out. When I'm grading, I'm looking for this notation, for you plugging in the numbers correctly, and then of course you got to calculate the answer. And now we'll talk about calculating the answer. Any questions on that much?
I might have missed it, but what does the mini 10 stand for before the C?
So, okay, let's talk about this C business. So first of all, I didn't derive the formula for you. That's one thing. And the second thing is, when we did the counting section, where I talked about the multiplication rule for counting, remember that?
Yes.
I also told you in that section that there was other counting techniques that we didn't talk about because we don't have time, so we skip it. Well, that C is one of the other counting techniques that we're not going to get to, and you don't need to worry about it. It's called combinations, if you've heard that before. If you haven't heard of it before, you don't need to worry about it. All you need to know is where is that button on the calculator, basically, is what you need to know. But 10C7 is something to do with combinations and counting.
Okay.
Okay, so let's see how to type this in the calculator. Okay, so first I'm going to type 10C7. This is the way you type it in the calculator. I'm only going to do one of these, so pay close attention, make sure you guys understand it. 10C7, what you do is you first type 10. Then you got to find the C. On the calculator, here's where it is. What you're going to do is you're going to push math. Okay, so here's math. Push math. Okay, let me cover this for a second. And then when you push math, you're going to scroll to the right to where it says probability. Now, some of your calculators, it might just say PRB instead of PROB. That's fine. And then go to the third one that says NCR. That's the C that we want. So go down to there and push enter. Now, it might not display it on the calculator like that. That's okay. Just type the 10, then the NCR, and then the 7, and then get the answer. So if you got 120, then you're good on that. So 10, push math, scroll to the right to probability, scroll down to NCR, push enter, and then push 7, push enter. That's 120. Is everybody following me on the 120?
Yes.
Okay. After you get that answer, now we have to multiply by 36 over 52 to the power 7. So now I'm going to push times. I'm going to open a parentheses, 36 divided by 52, close the parentheses, and then power 7. The power button on your calculator is right here. It's this caret or this hat symbol here, right above the division sign. Power 7. And then what I like to do is I like to get the answer to that much. So there's the answer. That's not the final answer, but that's the answer to that much. So I like to just do each one separately. So I do this one first, then I do times this, get the answer, and then I'll times this. Is everybody with me so far?
Yes.
Yes.
Okay. Now I'm going to do times again. So it's going to take the previous answer times 16 divided by 52. And then power, I'm not going to type 10 minus 7. You could, but you got to be careful because it might do it wrong. So I'm just going to do 10 minus 7 in my head. That's 3. So I'm just going to do power 3. And that's the answer to this problem. 0.266. I'm going to write 0.2665. I'll round to 4 digits after the decimal point. 0.2665 for that one. If you understood how to type that in the calculator, then all the rest of them are going to be similar. There might be a little more work to do, but that's basically the idea there. Okay, questions on part A? No? Okay, so let's go ahead and look at part B then. What is the probability that you draw between 6 and 8 number cards inclusive? Okay, so to do this one, see, part A and part B, how are they different? In part A, I just said exactly this many number cards. There was just one answer there. 7 number cards, and that's it. This time, I'm giving you more than one possibility here. Okay, so it's 6. What does it mean to be between 6 and 8? To get between 6 and 8 number cards means you get 6 number cards, or 7 number cards, or 8 number cards. Did you hear what I just said? Did you hear how I said or? Again, I'm asking what's the probability of getting between 6 and 8 number cards? That means 6 or 7 or 8. What that means is this problem is going to require the OR formula. Okay, so not a big deal, but we're going to have to use the OR formula. So it's going to go like this. You're going to write down the notation first. Probability x equals 6, or x equals 7, or x equals 8. I don't know why. For some reason in this section I use the word or instead of this symbol for or. You can use whichever one you want, but I usually use the word or in this section. That's what it means to be between 6 and 8, 6 or 7 or 8. Also, I guess I should talk about the word inclusive real quick. Because there's two meanings for what between means, okay? When you say between 6 and 8, could 6 and 8 be possible or not? So if you say something is between 6 and 8 and it's not 6 and it's not 8, but it's between, then it would have to be 7. But if 6 and 8 are possible, then it's 6 or 7 or 8. So if you say inclusive, that means include these as being possible. So they're going to be possible results. If they ever write exclusive, then you're not going to use 6, you're not going to use 8, you just use whatever's in between. Okay, so between has two different meanings in English, so inclusive makes it more clear. Okay, we're going to have to use the OR formula. I know there's two OR formulas depending on if the events are disjoint or not. When it comes to random variables, though, the events are always going to be disjoint. Different values for the variable are always disjoint, because no two of these can happen at the same time. Could you draw 10 cards out of a deck of cards, and both of these things happen, meaning you get exactly 6 of them being number cards and also exactly 7 of them being number cards? No, they can't both happen. Either you get exactly 6 or exactly 7. You can't have both. When it comes to 3 events, if you want to see if they're disjoint, you have to look at all pairs. So let's look at this pair. If you draw 10 cards out of a deck of cards, could it be possible that you get exactly 6 number cards and also exactly 8 number cards? No, it's not possible. And same thing with 7 and 8, they cannot both happen. So these events are disjoint. So you're going to use the shorter OR formula, which goes like this: probability of the first plus probability of the second plus probability of the third. So you're going to write down the notation, then you're going to write down the OR formula. But now, each one of these looks just like this. So you got to do 3 problems just like part A now. And you just fill into the formula. So I'm going to do that real quick. For probability x equals 6, it's going to be 10c6, 36 out of 52 to the power 6, 16 over 52 to the power 10 minus 6. It basically looks just like this, but instead of all the 7s, I have 6s. Plus, now probability x equals 7. Well, I'm going to copy exactly this down. 10c7, 36 out of 52 to the power 7, 16 out of 52, power 10 minus 7. Then I'm going to do it again for the next one. So it's just, again, 3 problems like part A. The next one is 10c8, 36 out of 52 to the power 8, 16 out of 52, power 10 minus 8. And now you calculate each one of those. Now, one thing I do want to mention, when I'm grading, I'm looking for everything that's here. Okay, I'm looking for the notation or formula. Then plug all the numbers into the binomial formula and then calculate them all. So make sure you show me everything that I'm showing you here. The middle one we already did, so I'll just type that one down. I'll write that one down, 2665. I'm going to do the other ones on my calculator real fast without showing you, but you can do it afterwards to double check it. Okay, so this one is 0.2072. Let me do the other one. This one is 0.2248. And then you add all these up. And the answer is 0.6985. Questions? Okay, and again, it doesn't get much harder than that. If you understand part B, let's go to the next one. Was it probably draw at least 8 number cards? Well, you're going to have to rephrase this, but what does it mean to get at least 8 number cards? At least means 8 or higher. So at least 8 means 8, exactly 8, or tell me the rest of it. So if it's at least 8 number cards, it's 8 or what?
Or 9 or 10.
Or 9 or 10. You have to stop at 10 because we're drawing 10 cards total. You can't get more than 10. So if you're going from a number up, you go from 8 up to whatever n is. If you go down, if it says at most 8, so that's 8 or less, you would go down all the way to what number? What's the lowest number it could be in a binomial problem?
0.
0. Please don't forget that. People often forget the 0. Okay, now this is identical to the last problem. You just do probability x equal 8 plus probability x equal 9 plus probability x equal 10 using the OR formula. Then use the binomial formula for each part. So it's going to be 10C8, 36 out of 52 to the 8, 16 out of 52 to the 10 minus 8. Next one is 10C9, 36 out of 52 to the 9, 16 out of 52, 10 minus 9. Next one is 10C10, 36 out of 52 to the 10, 16 out of 52 to the 10 minus 10. And once again, you'll calculate these three things and you'll add them. Let me see where the next problem is going to start. Okay. So again, you just calculate these. The first one, the 10C8 one we did already. It's over here, 0.2248. All right, let me do the rest of them. This one is 0.1124. Again, you can double check it later. The other one is 0.0253. And then you add them up. Okay, that's part C. Questions on part C? Well, if you didn't have questions on part B, then part C is almost exactly the same thing. Let's go to part D. What's the probability that you draw at most 7 number cards? What does it most 7 number cards mean? It means 7 or what? Anyone?
Or 6 or 5 or 4 and so on.
Right. So 7 or less is what it means. At most 7 means 7 or less. 7 or 6 or 5 or 4 or 3 or 2 or 1 or 0, all the way down to 0. But if you write that out, that's like 8 terms. That's kind of nasty. But you can do it that way. You can do it that way where you write all 8 of them out and then do it. But there's a little trick that I want to show you that works sometimes. So it's something to try. This is something to try if you have a lot of terms. Okay. What you do is you think about what the complement is. Remember what the complement is. The complement is the rest. It's everything else. So if it's not at most 7, so if it's not 7 or less, then what is it?
1 minus 7 or less.
Okay, that's how you find the probability, but let's not talk about probabilities. Let's talk about the event first. So the event here is at most 7, 7 or less. I'm saying if it's not 7 or less number cards, then how many number cards is it? So what I'm saying is if you draw 10 cards from a deck of cards and you don't get 7 or less number cards, then what did you get?
At least 8 number cards.
You got at least 8 number cards. You got 8 or 9 or 10. Look, these are all that's possible. This is the amount of number cards you can get. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This question is saying find the probability you get 7 or less number cards. What I'm asking is what's the complement of that event? The complement is everything else, at least 8, 8 or 9 or 10. But see, we found this probability here. So if you want to find this probability, since it's the complement of that event, the probability of this is 1 minus the probability of that. So instead of having to do 8 terms, you could just do 1 minus this answer and get the answer. So you guys with me that the complement of at most 7 is at least 8? Is everybody clear on that?
Yes.
Yes.
Okay, cool. So then the way you would write this again, that's why I asked part C, so that part D would be really easy. Okay, so the answer, so this is probability at most 7, 1 minus probability at least 8. So 1 minus the 0.3625, which is 0.6375. That's part D. Questions on part D? All right. Part E says find the expected value, standard deviation, and variance of this random variable. Again, normally these are not fun at all to calculate, but for binomial, it's very easy and very fast. So the expected value, the formula is, oh, that's not the, so the expected value is n times p. This is only true for a binomial random variable though. You just do n times p. N was written on the last slide, it's 10. And p is 36 out of 52. So you do 10 times 36 out of 52. And I'm getting 6.92 for that. To find the standard deviation, the formula for standard deviation, again, this only works for a binomial. The formula is square root of npq. So you just plug in 10 for n, p is 36 out of 52, q is 16 out of 52, and you square root this. Let's see. And I'm getting 1.4, it's 1.4595 something. I'm gonna round it to 1.46. And the last thing, to find the variance, you could either just square this, or you could just use the formula. It's this without the square root, either way. So it's 10 times 36 out of 52, times 16 out of 52 if you use the formula. The answer to that is 2.13. Look how fast that was. I mean, again, in section 6.1, it takes forever to find these things, but for binomial, it's very fast. Any questions on that? Okay. Part F says explain the meaning of the probabilities. Every time you calculate a probability, you should ask yourself what it means. So we've got to explain what the meanings of the probabilities are. And then we have to explain the meaning of the expected value. We'll do this one after. Let's do this one first. Okay, so for example, here's the first probability we found in part A. We found probability x equals 7. The answer as a percentage, whenever you're explaining the meaning, you want to write it as a percentage. It's 26.65%. Let me explain the meaning of this, and everyone just listen to it, then I'll write it down. What does this mean? Remember, when you explain the meaning of a probability, you got to say if you do something many times. What are we doing in this problem? We're drawing a card 10 times, right? So we're drawing 10 cards from a deck of cards. You got to say if we do that many times. Sounds a little bit weird. If you draw 10 cards from a deck of cards many times, okay? So it means you draw 10 cards. Imagine these are 10 cards. And then you draw another set of 10 cards. And you keep doing that. So you draw 10 cards, then you draw another 10 cards, then you draw another 10 cards, and you do it many times. Well, for this first set of 10 cards, you might have got 5 number cards. For this one, you might have got 8 number cards. For this one, you might have got 7 number cards. For this one, you might have got 3 number cards. Each time you're going to count how many number cards you got. And then if you look at these numbers, you're going to get 7 number cards. You're going to get this situation about 26.65% of the time. So the way to explain that is if you draw 10 cards from a deck of cards many times, you'll get exactly 7 number cards. That's what this says. You get exactly 7 number cards about 26.65% of the time. let me write that one down. Okay, so if you draw 10 cards, I'm just gonna write many times, you will get exactly 7 number cards about 26.65% of the time. So in the binomial problem, we're drawing 10 cards if you do that many times. Okay, I'm going to write down the other 3 probabilities. I'm not going to write down the answers. I'm just going to say them. But this one was between 6 and 8. So 6 or 7 or 8. And the probability here was 69.85%. So I'm just going to say it once so you can hear it. If I ask you to explain the meaning of this, you would say, if you draw 10 cards from a deck of cards many times, you'll get between 6 and 8 number cards about 69.85% of the time. Instead of saying exactly 7, you'll say between 6 and 8, because that's what the question was for that one. You get between 6 and 8 number cards about 69.85% of the time. The third one was at least 8. Right, at least 8. And that probability as a percentage was 36.25%. So if you're going to say that one in words, you're going to say, if you draw 10 cards from a deck of cards many times, you'll get at least 8 number cards about 36.25% of the time. So this is the event. At least 8 number cards about this percent of the time. And the fourth one that we found was probability at most 7. The percentage was 63.75%. So again, if I ask you to explain the meaning of that one, you would say, if you draw 10 cards from a deck of cards many times, at most 7 of them will be number cards about 63.75% of the time. So it's almost it's very similar to what's written up here, just the middle part, you have to mention what's in the parentheses because that's the event. And then just change the probability to whatever the probability is. Well, the expected value was 6.92. I'm not going to ever ask you to explain the meaning of the standard deviation or the variance, but I will ask you to explain the meaning of the expected value. We did that in 6.1, but how does that work in the binomial section? Again, it sounds a little bit weird, but let me say it. Expected value is calculated from probabilities. So again, you have to say if you do something many times, but we have to add a little bit to it. So remember how I was drawing the cards before? You draw 10 cards, and then you count how many number cards you get, like 8. Draw 10 more cards, you get like 3 number cards. Draw 10 more cards. Maybe this time you get 7 number cards, and you just do that over and over again. So the way you say it, I'll say it and then I'll write it down. If you draw 10 cards from a deck of cards many times, that's like this part. So like you draw 10, then you draw another 10, then you draw another 10, then you draw another 10. And then each time you count how many number cards you got. If you take the average of these, the average will be about 6.92. Because this number is right about 7, basically what that means is if you draw 10 cards, you expect 7 number cards. But if I ever ask you to explain the meaning, I don't want you to use the word expect. What does that mean to expect 7 number cards? It means the average of these answers will be about 7. Let me go ahead and write down how you're going to write it down. So if you draw 10 cards many times, and then each time, so in each group of 10, each time count how many number cards you got. So these numbers, and take the average. So if you did this 1,000 times, you would have to add all these numbers and divide by 1,000. The average, the answer you get, will be about this number, 6.92. Sometimes the students will write this as a percent. It's not a percent. Just write 6.92. It's not dollars. Don't write $6.92. This is how many times we got a number card. So those are whole numbers, and then we're taking the average of them. The average would be about 6.92. Okay, here we go. According to the CTIA, 25% of all US households are wireless-only households, meaning they have no landline, they just use cell phones for their phone calls, no landline. In a random sample of 20 households, what is the probability that, and then there's a bunch of questions. Okay, so this is a binomial question, but you can't really tell until you read one of the parts. So let's just focus on the first part for now. So it says, in a random sample of 20 households, what is the probability that exactly 5 are wireless only? Taking a sample of size 20 is kind of like doing something 20 times. It's like randomly selecting a house, then randomly selecting a house, then randomly selecting a house, doing that 20 times. So in that sense, we're doing something a fixed amount of times. Okay, so I'm not going to answer this question yet. Let's first think about the ingredients. Does this have the ingredients to be a binomial problem? Now, this is stuff you don't have to write on a quiz, but let's just talk about it first. So the first ingredient would have been, are we doing something a fixed amount of times? We'll call this the first ingredient. Again, you do not have to show this on a quiz or anything. And the answer is yes. We're selecting a household. "20 times. Okay, so that's the first ingredient. Okay, so the second one. So the second ingredient would have been each time we do whatever we're doing, well, in this case, selecting a household, do the outcomes land in only one of two categories? Okay, and the answer for this is yes. Every time we select a household, what are we going to wonder about? We're going to wonder if it's a wireless only household or not. So there's a success and there's a failure, and success is going to be if the household is wireless only. Now we're going to have to write something like that down when you start a problem in a few minutes, but we're just going through the ingredients first. Second thing, what's a failure? If the household, you can write isn't wireless only or has a landline, something like that. If the household has a landline, I'll write that down. Okay, so the second ingredient is working. Let's see about the third one. So the third ingredient would have been, is each trial independent of the others? In this case, I'm selecting a house 20 times. If I was selecting one at a time with replacement, so in other words, if the second household has a chance of being the same as the first one, this would be independent. Now, this is the part where we're going to have to fake it a little bit. The problem says we're taking a random sample of 20 households. When you hear something like that, usually it means that we're not selecting one at a time. Usually it means we're selecting all at once. And if you select all at once, then the individual households that you selected are not independent of each other, because this, if you put them in a list or something, the second household has no chance of being the first one, so they're not independent. So the independent part is a little bit iffy, but I'll say two things. Number one, for problems in this section, just ignore it. But if I had to give you a better answer, the better answer would be that down the road I'll probably mention, so I guess I'll mention it now since I'm going to mention it down the road, that if you're selecting a sample that has a small sample size, something like 20 households, out of something that has a really big amount of things to select from, then whether you do it with replacement or without replacement, probabilities are going to be almost the same. So things are going to be very close to independent. In other words, yeah, the second house, okay, what are we selecting from? We're selecting from all houses in the US, all households in the US. How many are those? How many households are there in the US? Oh, I don't know, 100 million, something like that. And we're selecting 20. So we have a huge amount to select from. We're only selecting 20. So if we were selecting one at a time with replacement, yes, the second household has a chance of being the same as the first household, but it has almost no chance. It's, 1 out of 100 million chance that the second household we select is the same as the first one. Whereas when we select all at once, the second household has no chance of being the same as the first one. Whatever, 1 out of 100 million is almost 0. So even though technically this is not independent, it's very close because the probabilities are almost the same. So later on in the class, I'll tell you that if you're selecting a small sample out of a huge sample space, then no matter which way you sample, independently or dependently, in other words, with replacement or without replacement, probabilities are going to be about the same. So we can just assume independence. So that's a little bit of me faking it, but we're going to say, okay, kind of. Okay. So then let's go to the fourth condition. So the fourth ingredient for it to be a binomial was the question has to ask you to find the probability of a certain number of successes. And that's what they're doing here. They're asking, remember, success was if the house is wireless only, and they're asking to find the probability to get exactly 5 of the 20 being wireless only. So that's exactly it. Find the probability of this many successes. So yes, that's definitely what they're asking in part A. So this is binomial. Okay, so now that it's binomial, now that we know it has the 4 ingredients, here's what you actually have to write. Okay, so when you recognize it's a binomial problem, the first thing I want you to write down is the word binomial. And then you're going to write down what n is, what a success is, what a failure is, what little p is, what little q is, and then what capital X is. Okay, n stands for how many times we're doing whatever we're doing. Again, it's a little bit easier if you think of it as we're selecting 20 households, one at a time, with replacement. Okay, so n is going to be 20. That's how many times we're doing the thing total, so 20 times. Okay, then, when it comes to describing what these things are, you need to think about drawing once. Think about drawing once. In this case, think about selecting one household. I know we're selecting 20 in the problem, but imagine you select only one. So if you select only one household, how do you know if it's wireless only? Sorry, I said that wrong. If you select only one household, how do you know if you have a success? The answer is if it's wireless only, because wireless only is what they're asking about. So if the selected house, notice I'm saying the selected house hold, because I'm thinking about only selecting one, is wireless only. Okay, so then what's a failure? If the selected house again, you can write isn't wireless only, or you can write has a landline. I'm going to write has a landline. Okay, then we're going to write down P and Q and capital X. P, again, we're thinking about selecting one. If you select one household, what's the probability it's wireless only? The problem tells us it's 25%. Now, I don't know, for whatever reason, I see students do weird things with this 25%. Okay, if they write 25 over 100, it's not the end of the world. But you don't have to. You can write it as a decimal or something. I see sometimes students try to make the denominator 20. I have no idea why they're doing that. You don't need to do that. Just put 25% here. I'm going to go ahead and write as a decimal. So 0.25. Again, an answer I see sometimes is I'll see something like 5/20 because that's 25%, but they got this 20 as the denominator. So again, if you're doing that, I see no reason to do that. So you can just write 0.25. Okay, so let's go ahead and erase this. Okay, well then if that's the probability of selecting a wireless only household, when you select 1, what's the probability of not selecting a wireless only household? It's got to be 0.75 because remember they have to add to 1. So P is 25%, Q's got to be 75%, so they add to 100%. I wrote them as decimals, so they have to add to 1 when you write them as decimals. Okay, then when it comes to X, you have to again talk about not selecting 1 household, but selecting 20. And what's X going to do? It's going to count how many successes you have. In this case, it's going to count how many households are wireless only out of the 20. So X is going to be the total number of wireless only households among the 20 households selected. Yeah. Okay, so those are the 7 things you need to write down before you start any binomial problem. Okay, now I'm going to go ahead and do part A, but to do part A, I'm going to have to erase this slide. So it's probably be a good idea for you to write these numbers down. Write down that N is 20, P is 0.25, and Q is 0.75, because we're going to need to plug those into the formula when we use it. Okay, so now I'll finally answer part A. Okay, so to do this, we got to get the notation right. So probability that we have exactly 5 households being wireless only, it's going to be probability. X is how many wireless households you have. So X equals 5. So this is the notation. Again, remember what X stood for. It's the number of wireless households out of the 20. So this is the probability that the number of wireless households that you get out of the 20 that you selected is 5. Okay, now to figure out the answer, I'm going to write the formula above it. Here's the formula, the binomial formula for finding probabilities. So it's supposed to be a little x over here. The formula is NCX, P to the x, Q to the n minus x. So you just fill in now. N, we said on the last slide, was 20. That's the number of households we're selecting total. C, little x, is the 5 right here. So little x is 5. Then you multiply by P, which is, remember, 0.25. So the power of little x, remember, little x again was 5. And then times Q, which was 0.75, to the power of 20 minus 5. Okay, so you put that in the calculator and you get, looks like you get 0.2023. Okay, that's the answer to part A. All right, let's go ahead and look at part B. Okay, so now it says, once again, we're selecting 20 households. What's the probability that fewer than 3 are wireless only? So what does fewer than 3 mean? So that's another thing we got to work on. What does fewer than 3 mean? It means less than 3. So then how many wireless households can it be if it's fewer than 3? Well, it could be 2, or it could be 1, or it can be 0. Please don't forget about 0. So to do this one, the notation for the question is going to be probability x equals 0, or x equals 1, or x equals 2. Okay. Then because it's an OR, and I told you before for random variables and ORs, they're going to be in disjoint events. That means you can find the probability of each one separately and add them. So this is going to be probability of x equals 0. There's probability of getting no wireless households, plus the probability of getting exactly 1 wireless household, plus the probability of getting exactly 2 wireless households. Each of those now is a problem like the problem we did in part A, where you just plug into the formula. So I'm just going to go ahead and fill in all this stuff to the formula. The formula was NCX, N is 20, so 20C0. 0. Okay, then P was 0.25, so it's 0.25 to the power x, which is 0, and then 0.75 to the power of n minus x, 20 minus 0. Then you do that for each term. So now for this next term, all the zeros you see here, I'm going to write the same thing over, but all the zeros are going to change to 1. So this is 20C1, 0.25 to the power 1, 0.75 to the power of 20 minus 1. And the next term is going to be every 1 changes to 2 now, 20C2, 0.25 to the power 2, 0.75 to the power of 20 minus 2. Okay, so you put all that in the calculator. So for the first term, we get 0.0032. I'm just going to write all these numbers to 4 decimal places. So I'm going to be doing some rounding. Again, I don't really advise that you do that. I advise you put it in the calculator all at once and then write the final answer, so you only round once. But, you know, sometimes students have trouble typing this in the calculator, so I'm going to go ahead and write every individual answer. This one here, if you round it to 4 decimal places, it's going to be 0.0211. This one's going to be 0.0669. And when you add them all up, you get 0.0912 for this probability here. Okay, let's go ahead and look at part C. So here it says, what's the probability that you select at least 3 households that are wireless only? So one more time, we're randomly sampling 20 households. What's the probability at least 3 of them are wireless only? What does at least 3 mean? So at least 3, this means 3 or 4 or 5 or all the way up to 20. I'm supposed to put x equals, but this is not the work yet. This is just me explaining it. If I did that and I use the OR formula where I find the probability of each thing and add them, I'm going to get, how many terms is that? 3, 4, 5, that's 18 terms right there, which it can be done that way, but that's a lot of terms. And so I told you a trick, and I said, if you have a lot of terms, one thing to try, now it's not always going to work, but try it, is think about what the complement is. So what is the complement of at least 3? So what is left off this list? 0 or 1 or 2. Okay, maybe that's a little sloppy there. Let's just go ahead and write it like this. So at least 3, again 3 or, I forget the word or. 3 could be 3, 4, 5, 6, up to 20. The only thing that's left is 0, 1, or 2. And I'm asking for the probability of at least 3, so it means 3 or higher. The complement is 0 or 1 or 2. But that's exactly what we found in part B. Part B said find the probability of fewer than 3 wireless only households. So fewer than 3 was this one. So we already found this probability. So to find the probability of the event in the rectangular box there, it's going to be 1 minus the probability of the one that's circled there. Okay, so now we can go ahead and show the work for this. So probability at least 3. You're thinking about what the complement is. So it's equal to 1 minus the probability of fewer than 3 of the households are wireless. And again, we did that in part B. So the answer to that was 0.0912. And so if you calculate that, you get 0.9088. Yeah, so that answer could have been 18 terms, which again, you can try, or we just do that. Okay, let's look at part D. So again, we're selecting 20 households, and it's asking to find the probability that the number of households among the 20 that are wireless only is between 5 and 7 inclusive. So what does between 5 and 7 inclusive mean? It means that exactly 5 are wireless only, or exactly 6 are wireless only, or exactly 7 are wireless only. You have to include the 5 and the 7. That's what inclusive means. Okay, so the notation for that is going to be probability x equal 5, or x equals 6, or x equals 7. And now it looks very similar to what we did in part B. You're going to use the OR formula, which means you do the probability of each event separately, x equals 5, plus probability x equals 6, You do the probability of each one separately, and then you add them. That's what the OR formula says to do. And now you're going to use the binomial probability formula 3 times. So this is going to be 20C5, 0.25 to the 5, 0.75 to the 20 minus 5. That's the first term. Do the exact same thing for the other terms, but change all the 5s to 6s, and then change all the 5s to 7s for the last term. So this is 20C6, 0.25 to the 6, 0.75 to the 20 minus 6. Last term is 20C7, 0.25 to the 7, 0.75 to the 20 minus 7. And you go ahead and calculate each of those. All right, so it looks like we get 0.2023 for the first one, 0.1686 when you calculate the second one, 0.1124 for the last one. When you add all those together, you get 0.4833. All right, so that's how all that one goes. That's how all that one goes. That's how that one goes. All right, so let's go ahead and look at the next example. Or, sorry, the next part of this example. So it's saying determine the mean, variance, and standard deviation of the total number of wireless households. Okay, so anyway, so it's asking for the mean, standard deviation, and variance of this random variable. And we have formulas for that. Since it's binomial, it's very easy. The mean, the formula, or expected value. Mean, expected value, same thing. The formula is n times p. And n in this problem is 20. P is 0.25. And you get 5. So the mean is 5. Okay. Then we're going to do the standard deviation. The formula is square root of npq, so you just plug into the formula. So 20 for n, 0.25 for p, 0.75 for q, and then you take the square root of all that. And that gives you 1.936. Let's just say we'll round it a little bit. So okay, so our sigma is 1.936. But of course that is rounded. Okay, and then for the variance, there's a couple ways you can do it. You can just go ahead and square the standard deviation. You can square this number, but if you do it that way, square the number on your calculator. Don't just square the 1.936 because it's rounded a little bit. Or the other way to do it is to use the formula for the variance. The formula for the variance, sigma squared, is n times p times q. So you just plug in, and it's 20 times 0.25 times 0.75. Oh, sorry, no square root. Okay, and when you plug that in the calculator, you get 3.75. So the variance is 3.75. It definitely beats calculating this by making a probability distribution, and so making a large table, which in this case would have 21 rows, and then going and finding the expected value, standard deviation, and variance after that. It's 21 rows because the first column you'd put 0, 1, 2 up to 20. Then the second column you have to calculate 21 probabilities, then use the formulas for all these things. So this is much faster, but remember, you can only use the formulas that I used here, this formula, and this formula. You can only use them if it's a binomial random variable, which it is, so we're okay. All right, on to the next part. It says explain the meaning of the probabilities that you calculated in part A, B, C, and D. Okay, in part A, we calculated the probability that we get exactly 5 wireless households. And the answer was 0.2023, which is 20.23%. What does that mean? Well, what you want to say is you have to do what we're doing here. We're sampling 20 households many times. And if you say that, then exactly 5 will be wireless about 20.23% of the time. Let me say it once and I'll go ahead and write it down. So if you randomly sample 20 households many times, exactly 5 of the households will be wireless only, about 20.23% of the time. Okay, let's write this down. So if you randomly sample 20 households, because that's what the experiment is here, households many times. So you got to do the experiment many times. Okay. Then what will happen? The event will occur, the thing that I've circled here. Exactly 5 of the households will be wireless only. About 20.23% of the time. Okay, so that's how you explain the one we got for part A. Okay, what about for part B? So a lot of this is going to stay the same in part B and C and D. Let me go ahead and just underline the parts that are going to change. So this exactly 5 had to do with the event, and this probability had to do with what the probability was. So those things are going to change. Let me go and write down what part B was. Part B asks you to find the probability of fewer than 3 wireless households. And the answer was 0.0912, which if you write as a percent is 9.12%. So if I ask you what this probability means, remember again, you have to do this many times. So if you randomly sample 20 households many times, the first line is right. For the second line, I need to erase this. Not exactly 5 will be wireless only. Fewer than 3 will be wireless only. So that's what we're going to put there now. So fewer than 3 of the households will be wireless only, about, and then this number of course is going to change, and it's going to be 9.12% of the time. Yeah, just the 2 underlying things are going to change for all these. The rest of it's the same. Okay, let's go ahead and look at part C. Okay, so for part C, we calculate the probability that at least 3 households are wireless only households, and that probability was 0.9088, which as a percentage it's 90.88%. So what does it mean? Again, if you randomly sample 20 households many times, that's what the first line there is. Okay, now I have to erase this fewer than 3, because now the event is that it's at least 3. So we're going to write at least 3 of the households will be wireless only, about, and I got to change this because we have a new percent now, new probability, and you put 90.88% of the time. Yeah, that's how part C goes. All right, let's try part D. Okay, so for part D, we found the probability that you have between 5 and 7 of the households or wireless households, and this was of course inclusive. Between 5 and 7 of the households are wireless only. The probability was 0.4833. If you write that as a percentage, it's 48.33%. So what does that mean? Again, same thing. If you do whatever we're doing in this problem many times. So if you randomly sample 20 households many times, so I guess over here I have to write between 5 and 7 of the households. I guess I gotta get the word inclusive in there too, so a little more room. Between 5 and 7, and let me put the word inclusive here, inclusive, maybe in parentheses, yeah. of the households will be wireless only, about, and then, yeah, change this number again to the new number, 48.33% of the time. Okay, so that's how you explain the meaning of those probabilities. Okay, we got one more part. Now it's asking to explain the meaning of the expected value that we calculated. So the expected value that we calculated was 5. Again, a quick answer to this, which I don't like because it uses the word expected, so it's still making you wonder, well, what does expected mean? But let me give you this answer first. If you select 20 households, you expect 5 of them to be wireless only. But again, what does that mean? You expect them to be 5 to be wireless only. What if you get 8? What if you get 6? What if you get 18? Are those okay? What does it really mean to expect? What it really means is on average, mu is an average. So what it really means is if you do this many times, if you randomly sample 20 households many times. So think about it like this. You go to a house, see if it's wireless only or not. Go to another house 20 times. So we sample 20 houses, ask each one if they're wireless only, and then I'm going to write down how many are wireless only. So number of wireless only. And let's say for the first time, we get 7 are wireless only. Then we do it again. So another group of 20 households. And this time maybe 3 are wireless only. Then we do it again. So we look at 20 wireless only. We look at 20 households and see how many are wireless only. And maybe this time, maybe 11 of them are wireless only. And we keep doing this. So okay. So here's what we've done. We've randomly sampled 20 households many times. Then each time we counted how many were wireless only. And this goes down like this. And then if you take the average of these numbers, it's going to be about 5. So that's a picture of the situation. Now if I'm going to write it all out, yeah, my picture's so pretty, but I'm going to have to erase some stuff. So let me see if I can do it without erasing too much. Let's just erase this part here. Okay, so here's what you're going to write. You're going to write, if you randomly select 20 households many times. Okay, so before I finish, so we select 20 households, then we select another 20 households, let's select another 20 households, and we do it many times. Okay, then we want to count how many are wireless only in each group of 20. So now I'm going to write down each time you select 20 households, count how many of the 20 households are wireless only. Okay, so again, you count how many are wireless only here, count how many are wireless only in this group. So in this group, count how many are wireless only. In this group, count how many are wireless only. In this group, count how many are wireless only. Do this many times, and then take the average of these numbers. And take the average. The average will be about 5, since the mu is 5. So if you take the average of the numbers that I have here, plus, if you did this, 1,000 times and took the average of those 1,000 numbers, you expect the average to be really close to 5, about 5. Okay, guys, well, that is the end of example 2. I hope that helped you a little more understand the way binomial problems work. Study hard, do a lot of homework problems, get really comfortable with binomial probability problems, and I will see you next class. Bye.